Hello, in this video we'll be talking about the LAS Sound Event Detection Project for the December 2023 Research Symposium. Here is a brief table of contents in case you want to skip ahead to any particular part of the video. Sound Event Detection, or SED, is the detection and recognition of non-voice sounds in audio. These sounds can be as loud as explosions and as quiet as pen scratching. They include planes hurtling through the air, trains barreling down their tracks, and automobiles racing down the road, as well as birds singing, squirrels chittering, and leaves rustling. Military and police forces use it to detect gunshots, and self-driving car designers see its potential application in improving the car's performances in reacting to environmental sounds such as horns or sirens. Here at LAS, we have been pursuing sound event detection since 2022. In 2023, our goals were to finalize a baseline algorithm to detect mission-relevant non-speech sounds, assess the algorithm on data in the wild, create novel user interfaces, and implement it on the corporate network. Our baseline algorithm is quite straightforward and consists of a deep net fed by sound embeddings as features. Specifically, we're using the VGG-ish sound embedding algorithm created by Google as features and a multi-layer perceptron as the deep net. The algorithm produces labels and scores that the user can employ. Our current baseline algorithm recognizes 6 sounds in addition to none of the above and achieves less than 17% pooled equal error rate across the 7 classes. During our preparation of the algorithm for corporate implementation, we discovered that MLPs, the multi-layer perceptrons, are not guaranteed to behave consistently, which means retraining models using the same training data and same parameters could result in wildly different error rates. This scatter plot illustrates the results of 156 experiments we conducted to determine what DeepNet hyperparameters and architecture choices contribute to the differences in error rate. Each dot represents up to 10 repeated train test runs. The x-axis shows the minimum equal error rate, the EER, for the set of runs, and the y-axis shows the difference between the minimum and maximum EER. EER ranges from 0 to 1 and is the point at which false alarms and false rejects are equal. It is often used as a general-purpose error measure. Our goal was to find an architecture and hyperparameter combination that provided both a low EER and little difference across runs. In other words, we wanted dots in the lower left corner. This scatter plot shows the higher performing runs close to the lower left corner. None of the runs with more consistent performance also provided low EER, but we think it's low enough to still be useful. The summer and part of autumn 2023 were spent investigating this unexpected discovery, learning more about deep networks and using our new knowledge to create an MLP architecture with consistent performance. In 2022, our algorithm research used Google's audio set corpus for training and evaluation. However, in 2023, we wanted to assess its performance on more realistic data. We chose to use audio from video and U.S. presidential White House recordings to determine how well the algorithm worked with messy data. We started our assessment with the audio from video dataset used for another LAS project, I Reckon, but have not yet progressed to the presidential recordings. Here is a quick sample of video from that dataset. In order to inform both the technical development as well as support analyst reviews, SED investigated the usefulness of dimension-reduced spectrograms to visually display the sound segments. The ultimate goal of the UI is to enable analysts to see a visualization in which similar sounds are grouped together, whether or not a model is able to provide a label as to what the sound might be. If an analyst hears a sound in their traffic that is useful or meaningful to them for any reason, ideally they could then run a query and explore this visualization to discover other cuts in their query results that contain the same or similar sound. Or they could use the visualization to scan through non-voice sounds in their query results to potentially identify previously unknown sounds of interest. The current implementation is developed in Python and served to users as an interactive web page via Voila. Users are able to visualize the audio in a variety of different ways, including 2D versus 3D and as one 10-second chunk versus 10 1-second chunks. Users are able to interact with the generated scatter plot by scrolling around the data, zooming in, and filtering by labels. Hovering on a data point displays a variety of metadata, and clicking on it plays the audio sample. Our efforts in 2023 highlighted the complexity of MLP training, which produced varying results when training on identical data and identical parameters. While this shifted the 2023 goals and outcomes, it substantially improved the LAS's understanding of deep networks and challenges associated with transition to the corporate network. We have a baseline algorithm nearly ready for corporate implementation and a new visualization tool that's nearly ready for users to exercise. During the year, we also met with potential customers several times and learned that there's growing interest in our project. In 2024, we plan to improve our SED project by designing and creating a tuning algorithm that will provide a way for users to easily add new sound models to the algorithm. We'll test the baseline and tuning algorithms on messy data and make improvements as needed based on what we learn. For the visualization tool, we plan to integrate data uploading into the web page and improve its robustness by implementing a database backend, which will both enable data to load more quickly and facilitate data filtering and querying by a variety of metadata, such as creation date, data source, or label. Once completed, we plan to start user testing and work on implementing support for multiple users simultaneously. Thank you for listening to this video. In closing, I would also like to thank Tina Kohler, the lead on this project, who is retiring in December of 2023 after many years of service to the government. After December 2023, if you have any questions or interest in this project that you would like to discuss further, please reach out to the rest of the team. Thank you.